Welcome to today's webinar. Thank you for joining us. This is an update of a webinar that Matt Schroeder and I did about 6 years ago. We actually did it as a seminar. Our objective is to outline the process that we've used successfully since 1988 in doing environmental forensics. And we'll get going. As you have been told, I believe this is going to be about 45 minutes. And we'd like you to hold questions to the end. And if you don't want to speak up, you can send them to Alan Hahn at the email address given there. Because we're doing this remotely, Matt and I are in different places. You probably can see who's on the call, on the webinar. Please respect their privacy. We are recording the presentation part, but we will turn off the recording during questions. And one of the things I've noted is that there's a 2 to 5 second delay between what I see on my screen and what you'll see on your screen. I'll be starting off and then Matt will join in at certain parts of the webinar. So what is environmental forensics? So by definition, environmental forensics is the systematic and scientific evaluation of physical, chemical, and historical information for the purpose of developing defensible scientific and legal conclusions regarding the source or age. Could you please make sure that your microphone is turned off? Thank you. So we're looking at the source or age of a contaminant released in the environment. And particularly, we're going to talk about our approach to the subject. So the topics we're going to cover today are robust conceptual site models, the importance of the multi-technique approach, problems we see frequently in forensic work, some very useful forensic techniques that we've been using the last few years, and we're going to go over 2 case studies. So our approach has been successful because of the things we're doing within our environmental investigations. We start with the fundamentals, things like Darcy's Law, things like transport of chemicals. We use multiple tools, and we do not depend on a single tool, meaning we try to, if you could, yeah, thanks. We try to use as many approaches to the question as we can to get basically a bulletproof conclusion. We consider independent and complementary data, and I'm not sure if that's something I just made up, but I'll explain to you what I mean by that. And then we use high resolution and high tech tools to help when we can. So our key is our conceptual site model process. And what we found is this truism: decisions, whether they're based for remediation or court or regulators, are not based on what is actually in the subsurface. Decisions are made based on the conceptual site model. So the conceptual site model is the key. So the conceptual site model integrates everything we know about a site, including site history, hydrogeologic information, release source and timing, and so on. I'm not going to go into all of them, and we're not going to talk about all of those in this webinar, but it has to include everything. So think of it as a puzzle. We have to put the puzzle together. The first, or basic, conceptual site model is similar to a phase 1 environmental site assessment. It consists of literature review, records review, air photos, and interviews. But you would want to go further in a forensics case, that you'd want geologic framework, groundwater flow conditions, soil and groundwater chemistry distributions, and contaminant transport processes. That's kind of like a phase 2, maybe an advanced phase 2. But we like to take it to the next step. We call it a robust conceptual site model, where we add other techniques: geophysics, groundwater modeling, fingerprints, isotope, high resolution, high tech methods. So not every project has all of these, but the more you can get, the more pieces that point to your conclusion, the stronger your position when you go to court or go to the regulators. So this is what I meant by independent and complementary data to constrain the conceptual site model. Independent data are data that answer the question directly, but from a totally different angle. I'm going to give you an example in a minute. And complementary data constrains the answer without answering the question directly, and I'll give you an example of that. So typical question is, can a chemical get from point A to point B in a given time? So typically we use Darcy's law or some variant of it to figure out the groundwater velocity. Darcy's law takes into account the hydraulic conductivity K, the hydraulic gradient I, and the porosity N. So can we check that groundwater velocity with independent data? So one of the ways we can do it is by using environmental isotopes. This diagram down here shows the time trend in tritium and precipitation in Ottawa, Ontario. It's the same in most places, but Ottawa has one of the most complete records. And tritium is a naturally occurring isotope of hydrogen that occurs in water molecules. Tritium peaked about 1,000 times higher concentration in 1963 than its natural levels. And this was due to atmospheric testing of atomic bombs. 1963 was when the Atmospheric Test Ban Treaty was signed. And since that time, the inputs into the atmosphere have been negligible. And besides that, tritium has a half-life, it's radiogenic, of about 12.3 years. That means every 12.3 years, it automatically decays or spontaneously decays by half. Excuse me for a second. So knowing this input function and the concentration of a groundwater, we can tell how old the groundwater is. So it gives us an idea of groundwater velocity without using Darcy's law. Another way is you can use a conservative chemical like chloride in a plume. Conservative chemical means that it doesn't react. It moves pretty much at the velocity of the groundwater. So you can figure out a velocity based on, say, chloride movement if you know, say, when a landfill was initially constructed. How far did the chloride from that landfill move? So that's independent data. You can also use complementary data. So are the geologic conditions consistent with calculated velocity? So how fast can groundwater move through this silty clay on the left? Does your Darcy velocity make sense? And is your Darcy velocity consistent with eyewitness accounts? Like in some cases, I'm going to talk a little bit about it later on, people actually saw a leak from a UST. So you know when it occurred. And there's also literature and interviews, and that would allow you to determine whether your Darcy velocity is consistent with your complementary data, or is it even conceivable? Like if your Darcy velocity comes out that your chemical was released in 1824, that's a bit problematic. So it's kind of common sense and complementary data. So there's lots of problems that we frequently see in forensic work. I've been doing it since 1988. Matt has been doing it since the early 90s. So we've seen a lot. And here's a few of the things that we've seen. Not understanding hydraulic conductivity measurements. Like hydraulic conductivity is similar to permeability. It's got the symbol capital K. And there's lots of ways you can determine hydraulic conductivity. There's field tests, laboratory tests, estimates, and they're all appropriate in the right case. But if we look at these two figures, the one on the left shows fractured limestone. Imagine if this fractured limestone was under 30 meters or 90 feet of soil. You would never know exactly where these fractures are. And you could drill 100 boreholes and not hit one of them. On the right, this is called the barbed clay. This is a glacial lake clay. And if you were to do a laboratory test like grain size distribution or something like that, you would lose this structure that is common in barbed clays. So you need to know how the hydraulic conductivity was measured and whether it was appropriate for that purpose. Not recognizing the importance of fractures. We typically think of clay soils, like we see on the left, as being impermeable. We use clay soils for landfill liners. We use clay soils for sealing wells, but clay soils can have fractures, especially in the lower Great Lakes area. We have fractures, and in this test pit where we were looking to see the nature of the clay, you can see these wet areas, and that groundwater is coming up in those fractures. So groundwater can move a lot quicker in fractured clays than it can in massive clays. The problem is that these fractures are vertical. So you need to be able to intersect them with a borehole that's vertical. You have some problems, and there are ways to get around it. Or if we look at this road cut in rock, if we didn't have this road cut, we would never recognize this fracture where the groundwater is coming on, or it'd be unlikely that we would see it. So fractures are important. We need to be able to discriminate wells when we're looking at drawing maps. And we've discovered multi-million-dollar mistakes where people didn't realize that wells were in different aquifers or at different depths in the same aquifer. And they tried to interpret information from them, like chemistry or groundwater flow. Like groundwater flow, one of the factors is hydraulic gradient, and these water levels show a very steep gradient, but we really shouldn't be comparing these wells. So in other cases, we've seen wells put in where they're trying to determine if there's free product gasoline on the water table and the wells are too deep. You'll never see the free product. So we need to be able to get our wells right. Some fate and transport concepts are often misconstrued. So groundwater flow paths and the contaminants that go with them are always simple. That's a misconception. I like showing this slide. This is a USGS map of the meanders at the southern end of the Mississippi River. And this is showing the complexity of the soils that are there. This is in 3 dimensions. So trying to understand the groundwater flow path is not always simple. Dissolved DNAPLs, dense non-aqueous phase liquids, like TCE, sink in groundwater. DNAPLs can sink in groundwater, but dissolved DNAPLs, dissolved like TCE, will not sink in groundwater. It will flow with the groundwater. Contouring programs like SURFR always accurately portray the distribution of chemicals. Seen this many times where people take the output from SURFR, contours of chemistry in the groundwater, and think that that's reality, but SURFR doesn't take into account groundwater flow. So it really should not be used unless you check it out and it's consistent with your groundwater flow. Fingerprint chemical to evaluate transport moves at the same rate as all the chemicals in a problem. And we had a case in Indiana that we worked on a number of years ago where the other side used some esoteric additive in gasoline to show that their gasoline release couldn't get to point B because their fingerprint chemical didn't. But when I looked at it closer, this esoteric chemical was severely retarded, meaning slowed down relative to the transport of chemicals like benzene, toluene, ethylbenzene, and xylene. So although that chemical didn't get to point B, their benzene could have easily gotten to point B. Then the actual source of a contaminant that's always the closest potential source. We see this all the time. And it's even better when that potential or the closest potential source has deep pockets. So these are misconceptions that we commonly see in our investigations. What you see is what you get. And this is where isotopes come in. Isotopes, we'll talk about a little bit later on, allow you to look at water, for example, and differentiate between different masses of water because you can look at parts of the water molecule, parts of the atoms in the water molecule, and know that they're different from other masses of water. So the forensic techniques we'll discuss today are groundwater modeling, fingerprints, isotopes, and some high-resolution site characterization. And Matt is going to take over here.
Okay, just give me a second to get set up here. All right, so I'm going to talk a little bit about groundwater monitoring or modeling example. So I'll give some basics on modeling and how we use it as a forensic tool. and then go through a model that we did a few years ago that where we looked at fuel release. So there's lots of questions that you can answer through groundwater modeling, including, who's responsible for a release, when did it occur, some of these other things on the screen here. And what model you use and how you construct that model is often dependent on what questions it is that you want to answer. So some of the considerations we have are here on the screen, and my general philosophy is to use the simplest model that can answer the question you're asking. So some of the things that we need to consider are whether the transport processes like degradation, diffusion, and retardation important to the flow system. Is the flow system complex or is it fairly simple? So that'll help you define how many dimensions you need to consider in your model. And then do the flow and transport conditions change over time? That'll let you know whether you need to include a transient model. These types of things are why the conceptual site model is so important. It's because that conceptual site model will tell you the answers to these questions. As far as the model code itself, numerical models can often be more powerful, but analytical models can often be simpler and maybe easier to use than a numerical model. There's lots of choices out there, models, probably hundreds. Probably the most common one is called ModFlow. And in this example, that's the model that we used. So in this case study, we used a ModFlow model to simulate a UST release and then used that model to help optimize the design and the remediation. So on the left is our conceptual site model shown as a block diagram. And you can see that we have a sand and gravel zone above a fine sand where the water table is located, underlain by a sandy clay aquitard. The right-hand picture shows the groundwater flow map, and you can see by the arrows that it flows away from the building towards the gravel pit in general. We see two UST areas shown by the red boxes. One is a single tank and the other one is a tank farm. We have residential areas to the south, which is to the right, and then also to the east, to the top, and those green dots are residential wells. So as part of the model, first we try to match the flow conditions, and that's called calibration. What we're showing here again is the observed flow. And then on the lower right, you see the modeled flow. Comparing the general shape of the contours, you can see that the spacing and the shape is pretty similar, so we're simulating the flow reasonably well. In order to get a more objective view, we also look at the observed heads compared to the modeled heads. And so that graph you see with the line going diagonally upwards, that would be a perfect match if all the dots fell right on that line. And you can see that they're fairly close. We also used some statistical analysis to compare the modeled heads to the observed heads in an even more objective way, and usually compare that to our calibration targets that are set up for the modeling effort. So another way that we can check the model calibration is to look at the transport within the plume compared to the known extent of the groundwater plume. In this case, we knew the timing of the releases from the two UST areas, and we used a tool called particle tracking where we can drop particles into the model. And you can see the little red dots are where we dropped particles in, and then you can, over time, see where those particles are transported by the red lines. In this example, you can see the particle tracks match the plume extent reasonably well. So that's another confirmation that our model was well calibrated. Once we have a calibrated model, we can use the particle tracking tool to aid the remediation design. In this case, our objective was hydraulic control using pump and treat. So we dropped particles around the edge of the plume this time, and we were able to evaluate the number of extraction wells and the pumping rate needed to be able to capture the plume. So a little earlier, I talked about analytical models. Another type of model we can use to evaluate contaminant transport and remedial options. This one I'm showing is called REMChlor, and it's an Excel-based model that can be used to model contaminant transport over time under different transport conditions. One use of this model that's particularly helpful is to evaluate the effectiveness of a source remediation on a downgradient plume. Using this type of model, we can quickly evaluate cost effectiveness of different strategies for source remediation. So this is an example of the output from REMChlor. It's showing contaminant concentration on the y-axis versus distance on the x-axis at a time 70 years after the model start. So by looking at this type of output over time in the model, we can estimate how long it will take for the concentrations to drop below the cleanup criterion at the property line, for example. From here, I'm going to hand it back to Mike, and he's going to talk a little bit about fingerprinting.
So fingerprints are diagnostic traits to distinguish between releases, and they can be specific chemicals, they can be groups of chemicals, chemical ratios, or isotopes. And I'm just going to quickly go over some of these. So specific chemicals would be like lead or MTBE in gasoline. We know that leaded gasoline was used before 1990. We know that MTBE, an additive in fuel to replace lead in fuel, was used between 1986 and 2003. So we can use the presence or absence of these additives in gasoline as indicators of the age when the release occurred. We can also use groups of chemicals. You may have seen these. These are chromatograms. These are from Jim Dragun's textbook, where you could look at the output from the chemical analysis, and basically what you see are fingerprints of the various chemicals in a fuel, and you could identify whether you have, say, regular gasoline or fuel oil or aviation gasoline. You can also use it to distinguish between fresh fuels on the left and weathered fuels on the right. Weathered fuels have lower and smoother peaks. Or you can do ratios. For example, this is one that I like using, call it the BTEX age. It's the ratio of benzene plus toluene divided by ethylbenzene and xylene. And this is useful because it is commonly available information at gasoline release sites. So according to this, this technique, if RB is between 1.5 and 6, the release is 1 to 5 years old. And if RB is less than 5, you've got an older release, greater than 10 years. And this example is a site we worked on where we knew exactly when the release occurred, and this worked very well and actually helped us to identify that there was a second unrelated release contaminating this property we were looking at. So next we'll look at environmental isotopes. Environmental isotopes are atoms like oxygen, hydrogen, carbon, and chlorine. Most elements have isotopes. All elements have isotopes. And environment or isotopes are basically atoms like oxygen, that have the same number of protons in the nucleus, the center of the atom, but they have a different number of neutrons, which are neutral particles, but protons and neutrons have the same mass. So if you have different numbers of neutrons, then the atom or isotope will behave differently due to those mass differences. So you can have, for example, hydrogen with no neutrons, hydrogen with 1 neutron, and hydrogen with 2 neutrons. They would all behave differently in the environment. So in the water molecule, H2O, we have 3 hydrogen isotopes. We actually have 3 oxygen isotopes, but we typically only use oxygen 16 and oxygen 18. And we can use this information to identify recent, old, or very old groundwater, tens of thousands of years, or last week's storm. We can determine the percentage of groundwater in a stream. We can identify leaking landfills, and we can also identify aquifer connections. So useful to supplement our other approaches to groundwater investigations. Environmental isotopes and contaminants are also useful. One we've been using a lot lately is looking at isotopes in the nitrate radical. You can look at nitrogen isotopes and oxygen isotopes, and we can determine whether nitrate in groundwater originated from cow manure or chemical fertilizer. And the ag industry is particularly interested in this approach. We also have compound specific isotope analysis, CSIA, where we look at carbon, hydrogen, and chlorine isotopes in hydrocarbons or solvents. And we can use it for determining whether we have 1 or 2 sources, if the chemistry looks the same. I'm going to talk about this a little bit later. So Matt, I think you're up.
Yep. Okay, I'm going to talk a little bit about high resolution site characterization, and then show you an example of a case study. Where possible, and in particular in our forensic investigations, we really like to use high resolution site characterization tools to get a higher density of data. Tools like passive soil gas surveys and downhole direct read measurements like membrane interface probe or MIP, laser induced fluorescence or LIF, and a hydraulic profiling tool, HPT, can provide thousands of data points in a single boring without laboratory analysis or time delays. So those tools can help us focus at the area and depth where traditional drilling and sampling are needed, often saving considerable cost. So in this case study, we have a manufacturing plant with a known TCE source under the plant, and you can see the plant building on the picture on the left. The groundwater flow is towards the highway, as shown by the blue arrow. And in the conceptual site model on the right, you can see that the impacts are at the base of the upper aquifer, which is separated by a relatively thick aquitard from the municipal drinking water aquifer. The impacts in our case have migrated off-site and are part of a regional plume from multiple sources that's impacted the municipal aquifer. After about a dozen years of remediation and monitoring, most of the wells on our site showed a significant downward concentration trend, as shown in the graph to the left. Based on this and risk assessment that supported it, we proposed to mothball the failing remediation system and move to a monitored natural attenuation remedy. The regulators agreed in principle, but weren't comfortable with TCE concentrations at a well near the downgradient property boundary, shown by the tip of the yellow arrow. The TCE concentrations at this well had bounced around a little bit, but kind of near 30,000 parts per billion. They asked that we explain the source of these high concentrations and why they weren't acting like the rest of the site and declining. So in order to define the impacts better, we performed a passive soil gas survey. Passive soil gas can be a relatively inexpensive method to aerially delineate a source. In our case, we went at an upgradient of the high concentration well, which was kind of in the upper right portion of this yellow box. So this is an example of our passive soil gas grid. We can see a spacing of about 2 to 3 meters in our grid. So the samplers, the nice part about this, can be installed by a technician using a handheld drill rather than having to use a drill rig. So after drilling about a 1-inch hole, and you put it maybe 12 to 18 inches deep, the sampler is put down in the hole and sealed in there for 2 to 3 weeks. The material within the sampler adsorbs VOCs, and after the samplers are retrieved, they can be analyzed for the VOC content. So this is the results of our survey, and you can see it's done as a heat map where the higher concentrations are in the lighter colors and the darker colors represent lower concentrations. So the first question we were trying to answer was the source of the high concentrations. Were they actually connected to the source under the building? Were they a separate source? Could they have potentially come from the railroad tracks on the northern side of the property? And you can see, because they're an isolated bullseye, we confirmed that they're not connected to the source at the plant, and also not probably due to any impacts from the rail line. Unfortunately, passive soil gas can't give us information about the depths of the impacts. So the next step in our investigation was to do membrane interface probes near the hotspot to try and figure out where the impacts were vertically. Membrane interface probe uses a carrier gas circulated across a membrane in the probe tip and analyzed at the surface to generate relative VOC concentrations as you advance the probe. So you're getting real-time data. The green contours here show our passive soil gas concentrations, and we completed a line of MIP borings in the flow direction and also a line perpendicular to the flow direction. And from these MIP logs, you can kind of see that the impacts start at about 36 feet below grade and go down to maybe 42 feet below grade. Here's a close-up so we can see that a little better. And the aquitard is right at approximately that level. So you can see, according to the MIP, our highest impacts are just into the aquitard. We also collected soil and groundwater samples to confirm our MIP results. And the groundwater results here you can see match very well with the MIP results. We also did some dye testing for free product and found at our center point here that we had a little bit of free product about 1 meter into the aquitard. So we had NAPL not in the aquifer, but just below it. And then lastly, we performed some permeability and organic carbon testing near the hotspot to better define the TCE transport rate. So this shows our updated CSM following the hotspot investigation. We now know that there's a small, maybe 6 to 10 meter diameter hotspot within the aquitard, and TCE diffuses from that hotspot into the water that's flowing in the upper aquifer. Because the TCE moves very slowly, and we know that from the permeability and organic carbon testing that we did, the impacts don't extend to a distance where anyone will be exposed. And currently, for this site, we're just monitoring annually. At this point, I'm going to give the presentation back over to Mike, and he's going to talk a little bit about our second case study.
Okay, so this is a site that we did compound-specific isotope analysis on, and you know what? I need to zip through Matt's slides here. Here we go. And the problem was this: there was contamination on one side of the road, a hot spot, TCE. There was a hot spot on the other side of the road, down gradient from the one on the left side of the road. And chemistries were similar. The geology consisted of thin soil cover over fractured rock. No matter how many wells were put in on this property and the road and on this property, the regulators insisted that there could be unknown pathways, that is fractures, that we could never know, that we would never intersect. Therefore, the property on the left was responsible for the property, the hot spot on the right. Furthermore, there were no soil evidence in the property on the right to indicate that there was contamination. So we were asked to do, could we do something that would address the unknown pathways argument? So the first thing we did, these are just showing all the wells, is we did a passive soil gas survey, as Matt had shown. And we wanted to get high resolution coverage. And we had two kind of integrated grids. We had dense grids around the hot spot on either side of the road. And we also had elongated grid along the curb line. So we wanted to see if the hot spots were isolated. We wanted to see if there was contamination crossing the curb line. And this is the TCE output. And you can see obviously higher the hot spot on the west or the left side is totally isolated from the hot spot on the right side. Furthermore, there's not movement of contaminant across the road. We wanted to have another technique that didn't use kind of the standard groundwater flow approach. So this line of evidence was the compound specific isotope analysis for TCE. TCE was the main contaminant. And what this shows is the chlorine isotope and carbon isotope concentration of TCE from manufacturers. This is from the literature. There are two groupings that have been reported in the literature. If we could show that one of the hotspots had a different TCE, manufactured TCE, that would have been really easy. And then the other way we can use this is we know that as TCE biodegrades, as it moves from the source and goes along the groundwater flow direction, the lighter isotopes, both of chlorine and carbon, go to the daughter products like DCE, and the heavier isotopes stay in TCE. So there's a trend that you'd expect in the groundwater flow direction, regardless whether your source is here or here, that would go up and to the right. So that would allow us to determine if the sources were the same for both hotspots. So this is what the data show. So these are the data up here. The east side wells, the west side wells, roadway wells. So these potential sources are out of play. So all of the samples are biodegraded from these here, even though we don't know the actual concentrations in the sources. These are the groundwater is related to this grouping. And then what we see is, so these are potential sources. The down gradient samples, the ones furthest away from the west side of the road, are less depleted, meaning they're lighter than the ones on the up gradient side. This is exactly opposite to what you'd expect if there was one source. So we concluded based on this that we had two sources, two separate sources, even though the TCE and the chemistry looked the same. And it was consistent with the soil gas results. So our client demonstrated that they were not responsible for the hotspot on the east or right side of the road, hotspot B. So in summary, there are frequently flaws in forensic work. A robust conceptual site model, the multi-technique approach, bring more certainty to your forensic work. There's some very useful forensic techniques that go beyond what we typically use in typical environmental investigations. And we showed you two case studies that we've done fairly recently that help you to understand how the value of these techniques. So we are going to open for questions, stop recording, and we wanted to let you know that